I'll be here. I'll be here. I'll have a snack also.
Okay, thank you.
Ciao, ciao, ciao.
Ciao, ciao.
Good afternoon if you are in Africa or Europe, or good evening in Asia, and good morning to our speakers in this session from North America, isn't it? So I'm Zsolt Podolyak from University of Surrey, and I will chair this session. It's a beautiful workshop or school, or I don't know what we call it. So our first speaker is Stephen Yates from Kentucky, and he will tell us about a structure of stable germanium nuclei. So please, Steve, go on. Yeah, we can see your slides.
Okay, does that look okay?
Yeah, it looks perfect. Yeah, we can hear you as well.
Okay, very good. Well, first of all, let me thank the organizers for this opportunity. This is my 7th TASTE conference. I think I trailed only John Wood in participation. And one thing I would like to do is take this opportunity to thank my hosts in South Africa, including, of course, Nico and John Sharpie Schaefer, and the various people at the university, Robbie and Werner, Reggie, the Temba Labs and Stellenbosch, and everybody who's been so gracious during my visits. It's one of the reasons I look forward to returning. Today, I'm going to take a little bit different tack than what I've used in previous talks. Most of the time, I've talked about lifetime measurements and kind of a pedagogical approach for the students. These lifetime measurements ranged over 50 orders of magnitude, and I found them very interesting to give, very interesting to read on. Today, I'd like to talk about the structure of the stable germanium nuclei and how we study these with fast neutrons. To give you an idea of the fast neutron reaction I'm talking about, we have an instant fast neutron, and that is a fast neutron, and it scatters from the nucleus, and the nucleus of the neutron scatters, the nucleus recoils, and it cools by emitting gamma rays. Let me just show you that again, in case you missed the implications of this. But it looks very much like a compound nucleus or fusion evaporation reaction, and I would agree with that. That these energies, a few MeV, you can characterize it in the same way that you would a compound nucleus reaction. And basically in the reaction, we populate an excited state or various excited states, and they decay by the emission of photons. And you saw that those states have different lifetimes. You can get a lot of information from this reaction. Let me just show you, first of all, how we produce the neutrons. We use a small Van de Graaff accelerator, which produces protons. Those bombard tritium gas, and the reaction produces neutrons, which are essentially monoenergetic. And so this is a real advantage. Again, our accelerator is shown over here. Let me see if I can get a pointer. Oh, here's my laser pointer. So our accelerator is here, and the protons impinge upon the gas in the gas cell. You get neutrons produced. They scatter, of course, from our scattering sample. Heated up or excited, and then it's the gamma rays that are emitted that we're interested in. So that's our process. Now, we can take advantage of the fact that the neutrons don't experience a Coulomb barrier to bring in neutrons at any particular energy we want and excite the states with energies up to about that energy. And I've shown here 3 different spectra that are overlaid, one with 1.6 MeV neutrons, 1.7 MeV, and 1.8 MeV, and you can see the increase in yield of the states. And if you extrapolate the yields down to threshold, you get the energy of the emitting state. And then you can see in this case, it's a 2+ state, and this is a 0+ state. Let me show you another example of this, and specifically in germanium 76. There are 2 states that are very close together. It's been 0+ and 2+. And you can see from the data here, those are the points with uncertainties. You can extrapolate down to the threshold, about 2.7 MeV, but you also see that there's a big difference in the cross-section. The 2+ excitation has about twice or a little bit more cross-section than 0+. So we can get an idea not only of the threshold of the emitting state, but also the spin, the angular momentum. We can also measure angular distributions, just as you would in a compound nucleus reaction. And we can learn then about the multipolarity of the decay. In particular, you see that this is a 0+ state, and of course it is isotropic. The other piece of information we get is related to the recoil. Of course, in the scattering reaction, the nucleus recoils. With these low energy neutrons, the recoil velocities are not very high, but they are still useful to us. And if the detector, if you have a detector at some angle theta, then the energy that you see for the photon is the rest energy plus this shift. It's a well-known Doppler-shift. But the nucleus is recoiling into a viscous medium. That viscous medium is the other nuclei. And so it's really it's slowing down. So this is a time-dependent velocity. And we can rewrite this equation in the following way, where we have an attenuation factor, and this has the information about the nuclear lifetime. And again, to show some spectra, I show 3 spectra here, one at 40 degrees, that's our blue shifted spectrum, one at 150 degrees, that's our red shifted spectrum, and then 190 degrees. And you can easily see the shifts in the energies of the gamma rays or the emitted photons. And you also see that for the two peaks here, that the shifts are greater in this case than they are in this case. That's of course due to the fact that the lifetime here is shorter. And this is all described in the very nice work by Thomas Value and more recent work by Aaron Peters, which describes some possible what we call chemical effects. So we can use the Doppler-shift attenuation method to get lifetimes, again on the femtosecond or hundreds of femtosecond regime. And if we plot the energy of the observed photons versus the cosine of the angle, again, this is the equation we're looking at, you can get the slope of the line or F tau value. And if you know something about the stopping process, then you can extract the lifetime. And this is described again in references shown. So just to summarize what we can get from inelastic neutron scattering with accelerator produced neutrons, we have no Coulomb barrier. We can vary the neutron energy. We can probe the nucleus to any degree that we want. We have excellent energy resolution because we're detecting gamma rays. We could detect the scattered neutrons. They have information, but that's much more difficult. It is non-selective, basically statistical in nature. But we are limited by the angular momentum brought in by these neutrons. You're not going to populate high spin states with these reactions. And the information obtained, well, you get a lot of information. You get spins and parities, gamma ray branching ratios, transition multipolarities, multiple mixing ratios, level lifetimes. From all of these, you can determine the transition probabilities, and you can measure cross sections. Now, what are the disadvantages? Well, we're limited essentially to studying stable nuclei. This is not because the reaction cross sections are small. In fact, in most cases they're reasonably large, but it's due to the fact that our neutron fluxes are small. These are, after all, secondary reactions. And to make things simple, we would like to have large amounts of enriched isotopes. And I'll illustrate in a little bit why that is necessary. So the question we would ask is, why study germanium nuclei? One current question has to do with the existence of double beta decay or neutrinoless double beta decay. And I'll say a little bit more about that. These nuclei are also structurally interesting. It's a region where we have shape transitions, subshell closures, questions about the rigidity of the nucleus, whether it's triaxially rigid or soft, and shape coexistence. We've already had mention of shape coexistence in this conference. There's going to be more discussions of shape coexistence. It seems to be a very timely topic. So if we look at the germanium nuclei, we see that there are 5 stable nuclei for us to study. Germanium 76, of course, is the one that's most current interest. And that has to do, of course, with double beta decay. Let me just say something about beta decay to kind of orient you in this process. If we look at the mass 76 isobars, they are shown here. And of course, selenium 76 is the most stable of those. And if we have things produced on this side of selenium 76, then the positron emission electron capture decays would occur as follows. If you have things produced on the other side, then you're going to get beta decay. And eventually you're going to end up at germanium 76. And germanium 76 can't energetically, of course, undergo this transition to arsenic 76, but there is another decay mode possible, and that would be the double beta decay as shown here. And the question then is whether double beta decay occurs by the emission of 2 antineutrinos as shown here, or whether it can occur with the emission of no neutrinos. And the second process is the one which is being sought by a number of people. And this is going to give us an idea of whether the neutrino is its own antiparticle, and we can determine if we observe it the mass of the neutrino. Now there are a couple of large-scale searches for germanium 76 neutrinoless double beta decay, Majorana demonstrator project in the United States, the Gerda project in Europe, and you can see that they're basically similar in what they're doing in terms of the amounts of enriched germanium 76. There are plans to merge these projects into a larger project, a more sensitive search called Legend. And I don't have time to say more about that, but it's a very interesting technology. And the people who are doing these experiments are advancing the technology considerably. So if I would just summarize what is known about germanium 76 double beta decay into selenium 76, this process, the 2 neutrino process, is well known. You can see the half-life is known to about 5% number. This process has not been observed. I hope I've got the current limit on the half-life. It's over 10 to the 26th years. So this is a very rare process. And if we look at the neutrinoless double beta decay rate, it's shown simplistically by this equation, which has 3 terms. There's a phase space factor, which I'm told is well known and reasonably well calculated. There's a Majorana neutrino mass, which we would like to obtain if we observe this process. And then finally, there's a nuclear matrix element. And unfortunately, this is not measurable. So you have to obtain it from nuclear structure theory. And this is basically where our measurements enter in, because we'd like to examine the nuclear structure theory and not necessarily constrain it, but just see how good the nuclear structure theory calculations are by comparison to real data in nuclei in the region. Now, this is a description of the various calculated nuclear matrix elements for neutrinoless double beta decay candidates for 10 of the suggested double beta decay candidates. The one we're looking at are here. And you can see in going from things like quasi-particle RPA to the shell model calculations, you see about a factor of 2.5 or so in magnitude. And remember, this is squared, so this is going to lead to a large uncertainty in the decay rate. So we'd like to constrain that, get a better idea on it. And to just say something about the structure of these nuclei, this set of calculations by Nomura and his colleagues shows for the germanium nuclei, and I've highlighted these stable ones in yellow here, that you get changes in the predicted deformations in the ground state. Of course, on this axis, we have prolate deformation. On this axis, we have oblate deformation. So the prediction would be that germanium-70 is oblate. By the time you get to germanium-76, it's expected to be prolate. Similarly, for the selenium nuclei, they've done calculations, and they get selenium-74 going from oblate. By the time you get to selenium-72, it's prolate. So there are changes in deformation here, and it's interesting how this is going to affect the neutrinoless double beta decay rate. Simplistically, if I just take those calculations and I look at what the structure of germanium-76 is predicted to be prolate, selenium-76 is predicted to be oblate or maybe even spherical. This doesn't appear to me to be a very easy transition, and the more difficult the transition, of course, this means the longer the half-life, the more difficult the detection of neutrinoless double beta decay. So it's important we take into account these calculations in selecting the experiments to do. And after all, these experiments typically are running hundreds of millions of dollars or hundreds of millions of euros. So it's important to have some input from the calculations. Now, we have done measurements on germanium-76. I just show here briefly the results. The experiment is shown here. Two different shell model calculations by Alex Brown are shown along with it. The widths of the arrows correspond to the magnitude of the BE2s, and the description is pretty good. We've also, as I mentioned, studied selenium-76. In this case, I compare to Nomura's calculations. Again, the description is pretty good, but how good is good enough? We'd really like to constrain these calculations in a better way. And what I'm proposing, I call a comprehensive approach. And let me just describe what I mean by that. First of all, I think we'd like to identify all of the excited states up to some energy, maybe 3 MeV or so. Once we start breaking pairs, of course, things get very complicated. And we'd like to do this in as many nuclei in the region as possible, but certainly those near the nucleus of interest. And we're going to assume that what we get with our inelastic neutron scattering reaction is a statistical population of states. We'd like to eliminate what I call erroneous states, and I'll describe what these look like in just a minute, but these are states that are incorrectly placed in the literature. We'd like to characterize all of the remaining states fully. And I seem to be getting a little bit of noise in the background. I hope it's not too annoying. But so we'd like to characterize all of these remaining states fully. And that means we'd like to determine the spins, the branching ratios, the mixing ratios, the lifetimes, and the BE2s. And we'd like to compare these data with theoretical model calculations. When we compare with the theoretical calculations, we expect a 1-to-1 correspondence of the theoretical states with the experimental states. And so if we look again at the germanium nuclei, recall that we've looked at germanium-76. Where would we go next? Well, germanium-74 looks like our best candidate. And it's attractive for several points of view. First of all, it's the most abundant of the stable nuclei, stable germanium nuclei. And you can see that germanium-73 is also stable. That means that we can do transfer reactions into germanium-74. We can do neutron capture into germanium-74. So it has a number of advantages. So that's the nucleus that we decided to study next. And how well we can characterize that is important in terms of what we can say about the nuclear structure calculations. Now, this just shows a NN prime gamma the spectrum, and I show this so that you can see what high quality the data are. You can also see the size of the scattering sample. It's 19 grams of very highly enriched material. And so this is what we require for our measurements. And this shows a comparison on the left of the data and Alex Brown's shell model calculation on the right. Now, Alex did these calculations before we had done the experiments, and so there's no adjustment in the theory. But one thing you'll quickly see is that there are more experimental states combining our data with the NSDEF compilation than theoretical states. That's really quite amazing. And one of the problems we have, of course, is that frequently states get placed and they are just wrong. And so if I get rid of the erroneous states, and those are the ones that are shown in red, then those are states that are just wrong, and we want to get rid of them. So I get rid of them. Then I do a comparison of the experimental states and the theoretical states. There's a very nice one-to-one correspondence. So this is very successful. The other thing we'd like to say is, what about the transition rates? What about the characteristics of these states? There should be not only corresponding states, but their characteristics should match. And so this shows, again, a comparison with calculations from the shell model. And you see on each of these boxes, there are two numbers. The upper number, the one with the uncertainties, is the experimental number. The one below is the theoretical number. And you can see that the agreement is really spectacularly good. Even for the M1 scissors mode, or mixed symmetry state shown here, the agreement is really quite impressive. And so let me just summarize how I think we have done for germanium 74 in approaching my goal of a comprehensive approach. I'd say that we have identified all states below 2.5 MeV, probably up higher, but probably not all of those below 3 MeV. The many erroneous states below 3 MeV we have eliminated. The lifetime of only one state below 2.8 MeV was not determined. The only thing we could determine in that case was a limit. And the spin parity of one state below 2.8 MeV we could not assign, but the agreement with the shell model calculations is in place. So I think this is a good approach. Of course, we want to do other measurements on the germanium nuclei and basically solidify the approach in terms of the theories that would explain this. Now, germanium 76 is not the only neutrinoless double-beta decay candidate we've studied. We've also studied a number of others, including, you can see tellurium-130. Sally Hicks is going to talk about that in a couple of talks. And you can see others that we have studied by this approach. Okay, with that, I'd like to just close by saying something about shape coexistence. Shape coexistence is something that where we have occurs when we have states of different deformations in a single nucleus. And the regions of shape coexistence from the review paper by Chris Haida and John Wood is shown here. And the region we're interested in is the germanium selenium krypton region is shown there. Shape coexistence in this region has been known for roughly 50 years. And it's interesting how all of this occurred. But usually when we look at shape coexistence, we look at nuclei either at closed shells or near closed shells, and we see what clearly look to us like rotational structures like this 0+ band or this 0+ band. And so it becomes very obvious. Or in the case of the lead nuclei, we have a structure that where these 0+ band come down lowest at the neutron midshell. This is a kind of a signature, a smoking gun for shape coexistence. Now, in the case of the germanium isotopes, we don't have that. And in fact, the shape coexistence in these isotopes was established essentially from nucleon transfer, two nucleon transfer reactions. And this is a very complicated picture at the top. This is from the review by Chris Haida and John Wood. And you can see that the horizontal arrows correspond to transfer, to neutron transfer reactions. The vertical arrows are to proton transfer reactions. And the diagonal arrows are alpha particle transfers. And from all of these measurements of the transfer reaction cross sections, the ground state and the first excited 0+ state, they were able to deduce the shape coexistence from these transfer reactions without really very much input from the structure in terms of gamma rays. But as we saw, there are several germanium nuclei that are stable. And this is going to allow us to study these nuclei, we would hope, and identify those band structures. Now, you can see that we even have some work by our chairman, which has contributed to this, our knowledge in this region. Joel seems embarrassed to see that, but
I didn't expect this.
Well, you can see that the 0+ states are identified, the lowest 0+ states. You can see that there are many candidates here for states that could occur with and form bands. The question is, what do we really know? And I was really shocked when I first started looking at this because it's not very much that we know in terms of the structure of these bands. The stable germanium nuclei are shown germanium 70 through germanium 76. We do have a BE2 here that would lead us to think that that might be due to shape coexistence. This BE2 is amazingly small, and I don't quite know how to interpret that. Recent Kulex measurements have led to a large BE2 here, which supports the idea. But the structure is really quite lacking. And so we, of course, looked at what we had learned in germanium 74, the study that I just described, and we observed what looks like a band of states. And this is the kind of structure that we would expect for shape coexistence. The widths of the arrows correspond to the magnitude of the BE2s. Now, the other thing that we had to question is, well, we studied germanium 76. Why didn't we observe a band in germanium 76 if it indeed exists there? So we went back to our germanium 76 data, and I show it here. This is our NN prime gamma spectra. And what we did is we summed all of the angles at a neutron energy of 3 MeV, and we looked for the missing transition, and it's clearly there. Okay? But you can see that the magnitude of these other peaks that go through the top of my computer screen, through the top of the building, and so forth. So we had to work very hard to observe that. The next thing is does it really have the right threshold? And when we look at the yield, we can see the threshold tells us this should come from the state of about 2.5 MeV. And indeed, this is the state that we see. The lifetime we had measured from our previous NN prime gamma work, and we can determine the BE2, although it has large uncertainty, it's certainly consistent with what we would expect for shape coexistence. So we can add that, and we're now getting a picture that seems to be consistent with what we would expect for shape coexisting structure. Now, we've got other work that needs to be done because we'd like to measure or determine at least as well as we can all of the properties of the spin 0 states, the 2+ states. That means mixing ratios, that means lifetimes, that means branching ratios for all of these things. It would be nice to have Coulomb excitation data on the other nuclei. It would be nice to have E0 measurements or internal conversion measurements. We've still got quite a lot to do. But it does look like the picture of shape coexistence is reinforced by these measurements, and we would hopefully get all of the information we need in order to do the mixing calculations and fully understand shape coexistence in this complicated region. And I do want to point out that when I'm talking about the 0 plus states, in each case, I'm talking about the first excited 0 plus state. When I'm talking about the 2 plus states here, it's the third 2 plus state in each case. There are, of course, other 2 plus states. Okay, with that, let me stop and just thank some of my colleagues. A number of people contributed to this work, those from the University of Kentucky. I'd particularly like to mention Marcus McAllister. Now, unfortunately, Marcus died last year. He was very instrumental in all of this work. The other people from the University of Kentucky who contributed recently are shown, and my colleagues from other places, of course. Alex Brown has collaborated with us in the shell model calculations. Mitch Allman is working with us on the mixing calculations, and of course, John has been an inspiration to us through all of that. So with that, let me just point out what Kentucky looks like about this time of the year. You can see it's a very pastoral scene. Spring is much different, but it's always nice. Let me thank you very much for your attention.
Thank you very much, Steve. Very nice talk. Sorry for these problems with the noise. I couldn't spot anyone who had the microphone on, so I didn't know what to do about it. So anyone has any questions? I haven't seen any question in the chat, but probably we have from the audience live. So if you have one, please unmute.
I put one in the chat.
Sorry. So go on.
So Steve, thank you very much. The Doppler-shift attenuation method. Sorry, I haven't used my voice yet today. This is the first time I'm talking.
But at least you're awake.
Yeah, it still works. Yeah, it's amazing. So this Doppler-shift attenuation method is a very powerful technique, and I really enjoyed seeing your data. I saw that you have the stated 2.8 MeV for which you have an upper limit. You just passed it. Anyhow, Ernie Warburton had developed what he called a variant Doppler-shift attenuation method in which you recoil into different Z material. And he has shown that you can actually push this measurement to the 1 femtosecond region. So I'm wondering, for the state that you have an upper limit, could you try the variant Doppler-shift attenuation method that Ernie Warburton developed many years ago, if some people still remember Ernie Warburton?
Oh, I remember Ernie very fondly. It's an interesting question because we're almost constrained that the stopping material is also the target material. Otherwise, we'd be mixing various isotopes or materials, enriched material with non-enriched material and whatever. In principle, it could be done, but it's very difficult experiment. But it's a good suggestion.
Thank you, Steve. We have some more questions, and you put a lot of physics into this, but there are still questions from Bill Walters asking about the role of triaxiality, and from Alejandro Algora about E-note transitions, if you would like to comment to those.
Have you received mine?
Well, sorry, I haven't seen yours.
Okay.
In the chat, if you send it to everyone, I can see. If you send it to the organizers, unfortunately, I cannot see. Yeah. That's why I haven't seen Mushe's comment either. So.
Okay.
But if you want, let's Steve say something about triaxiality and E-note, and then Alfredo, it's your turn after that.
Okay.
If that's okay.
I would prefer to avoid the question of triaxiality.
Okay, that's a good answer.
Bill, I'd be happy to talk to you about that. You know, triaxiality is frequently addressed in terms of the spacing in the gamma band. And I have a little bit of reservation about looking just at the spacing in the gamma band because the unnatural parity states, the 3+ and the 5+, don't mix with as many states as the other states. And so you might be deceived a little bit by the spacing. Other than that, I really have nothing to say about triaxiality. So,
what about E-naught?
E-naughts would be great. And in fact, this is usually one of the signatures of ShapeCoexistence that you would like to see. The measurements, our measurements of internal conversions are just not possible because of the large scattering samples we use. But we do have colleagues who are, I think, interested in measuring and already have some of the measurements performed. But we can't really contribute to that, but they are important.
Yeah, Alfredo has a question. Sorry, Alfredo, I missed your comment in the chat.
Don't worry. Hi, Steve. Just a question. Well, I fully agree with this message of try to benchmark the calculations, and and as you have shown, most of all the shell model calculations cluster in a value, and all the other calculations cluster in other. And this is a very, very interesting structured discussion. The question is about the quadruple moments of the two double beta decay, the spectroscopic quadruple moments of the two pluses. And related to that, the effective charges used in the calculation, because in my view, in our view, this space of the interaction is too small. You need to open up, at least for the neutrons, to get a bit of extra collectivity. If not, you really have difficulties to explain the quadruple moments of the two pluses, of the lowest two pluses.
I accept that as a comment.
Okay, so I think it's time to thank Steve again, and very nice talk. Thank you. We have to move on to our next speaker. It's Paul Garrett from University of Guelph, and we'll speak about ruthenium isotopes. Yeah, Paul, is all yours.